Yes? Okay, those of you who know Contino know that he likes to sit down the back and he usually falls asleep. So after the class he asked me, did you mention that those pions, those scalars, are actually fictitious? And of course I said yes. But what he was really pointing to was because this is a rapidly moving course, that if you want the technical heart of the renormalizability of that electroweak theory, I'm not talking about the pions or their self-interact, just the gauge aspect, the gauge structure, the couplings that are controlled by the gauge coupling. The fact that this is renormalizable really is the cleverness of these RC gauges, and it's as C goes to infinity that you get back the unitary gauge. Formally, you get back the unitary gauge. But the technical aspect is to really check that these fictitious particles, the pions and the ghosts, which get masses that go to infinity as C goes to infinity, that they truly decouple from the S matrix. This is the heart of technically saying everything that I said in a watertight perturbative proof. Okay. And the fact that they're fictitious particles, but the fact that particles where these masses appear in propagators that look like this, the fact that particles which are getting massive decouple from the S matrix, in even more physical cases, we understand this. This is a kind of decoupling theorem. The decoupling of heavy particles from the S matrix at fixed energies, C goes to infinity. Even for physical heavy particles, this is a kind of a technical statement which we can make more efficient by using effective field theory technology. But ultimately, it is a technical proof that heavy particles decouple from the S matrix. And here, these unphysical particles, which however, up to some details, just appear like heavy particles in the diagrams, you have to show decouple. And then, the moral equivalent of unitary gauge is achieved in this limit. And so this limit is not subtle in that sense. But you have to show that. And then, everything I said, which makes it look easy, becomes true. So I'm just giving you the overview, but the proof that this limit is not subtle is equivalent to the decoupling of heavy particles. Although in this case, they're these sort of fictitious heavy particles, the ghosts. Okay. That's one thing he reminded me of. And why did I wait? Anyway. You also reminded me it might be a good point to pause and ask if there were any questions. So some of you have come and asked me questions after the class, which is fine. Personally, I much prefer answering questions than giving lectures because I can never remember anything. But if provoked by a question, then I can talk about it directly. So, is there, I'll even give you a full 1 minute to pause, unless one of you already has a question. Yes, is there anything that is a little bit unclear there on the subject of the lectures? One question I have for you is simply, again, in talking to Contino, I find it's possible that all of you have seen almost everything I'm saying already, or the opposite? Because in the US, if somebody had just started graduate school, then they won't know it. They won't even know field theory, let alone any of these subtle stories. But here, it's all different. So I'm trying to gauge what is known to you, what is not known to you, even if it's, I'm assuming, let me say, I'm going on the plan that what I'm talking about, you've seen it in some form already, but I'm saying it in a slightly different order and trying to take a little bit of effort to say what is physical and what is unphysical, and what is the theorist's choice of weapons as opposed to what is the experiment, what is accessible to the experimentalist directly, what follows from general principles, and what happens to be experimental data. And given that it is life and death for us, which aspects of this story of the evidence are relevant as evidence in favor or against the existence of a gap? Meaning, we've discovered a heck of a lot of particles already. Is there going to be a big gap before we find the next one? Or many more to come? This is the burning, urgent question that we all face, and we have to look at what that evidence is. Okay. That was just to give you that 1 minute to think of the question. Et continue. I can proceed. Okay, good. Well, we left it at this point, which is fine. I just mentioned this aspect is all about what minor subtleties you could think of with the gauge interactions in this Higgs mechanism. But we see that even if the gauge interactions are extrapolatable to high energies, the price of this whole thing is these in these gauges where the pi's are actually visible as, at least to the theorist side, the pions are there. The pions are another word for those degrees of freedom that are most strongly interacting in the theory I wrote down, the so-called gauged nonlinear sigma model. But we are stuck. We have a nonlinear sigma model which implies non-renormalizable interactions, and the strategy for making it a renormalizable theory is to UV complete it, and that is if we could replace our nonlinear sigma field by a linear one, meaning one that sits in a vector space where you can add fields and get another field, then that would be good, because then we would be looking at something which could in principle be weakly coupled. So that's the job of linearizing the nonlinear sigma model. To do that, it's useful to just use the fact that SU2 left, to make it as familiar to you as possible, is secretly isomorphic to the group SO4, just as with all the same kinds of subtleties as this group is isomorphic to SO3, this group is isomorphic to SO4. Okay. You can play with the Lie algebras of both and easily check that out for yourself. But so I want to use this language. In that case, the breaking that we talked about to this diagonal subgroup, that spontaneous symmetry breaking that we see in the nonlinear sigma model, corresponds here. You can think of it like this. Okay, this diagonal thing is just SO3. This breaking is very easy to visualize. Imagine the following picture. Here is a sphere, okay, and if we take points on the sphere, so this is the sphere S2 sphere. If you take points on the sphere, or unit vectors. So unit vectors in 3 dimensions correspond to points on the sphere. And obviously they are acted on by the rotation group SO3. But if you end up choosing a particular direction, unit vector, then that breaks, so a point on S2 breaks the SO3 and replaces it, but it doesn't break it completely. You can preserve the SO2 subgroup. Okay, so you're all familiar with that fact. And now, that was the analogy, not to be confused with the real thing, which is that if I replace this by the 3-sphere, so that's a picture of the 3-sphere, and I replace this by SO4, which acts on points of the 3-sphere, then a point on the 3-sphere breaks SO4 down to SO3, and points on a 3-sphere, that's exactly what the sigma field is. Remember, sigma takes values which are SU2 values. Sigma is constrained to be SU2 value. SU2 geometrically is nothing but the 3-sphere. So don't think of it as a group. As I said, distinguish the SU2 that is this field from the SU2 which is the gauge group. Distinguish them. Think of this sigma as just S3, the points on the 3-sphere. Of course it's acted on by SO4, okay? Just rotations on a sphere. And then any value of the field, whatever I choose to be its vacuum expectation value, and I can always set up my axes, so that's just the identity. So I align my axes with whatever this is. But whatever direction I choose will break SO4 in this analogy to SO3. Okay. So that's all that this is doing. And so that means that this 2x2 notation, which you can go and work out yourself, is equivalent in this language. When you make this isomorphism apparent, you can switch languages from 2x2 language, which is a representation of this, it transforms under this, to fields, so these are fields. You can replace it just by changing your definition to a field which is a unit 4 vector. Of course, I don't mean in real space-time, I mean in this isospace-time. Okay? So, iso. Okay, some internal. So really, this nonlinear sigma model is this. Of course, it has 2 derivatives. It has 2 derivatives and it's SO4 symmetric. The Lagrangian is SO4 symmetric. So it could only be this, where this arrow, of course, is again an iso vector. If you want. Ni, where I goes from 1 to 4, but where Ni, so instead of being a field that you can add and subtract, you can add linear combinations, this thing is constrained to be a unit vector. It's constrained. And hence, it is just as badly behaved as this language. In fact, it's the same theory, just written. So you can work out what that translation is yourself, but it must be that secretly we're talking about this theory. Okay? Once you do that, we want to know how to linearize this theory. And it's obvious now how to do it, which is replace it. So the renormalizable version is to just write it like this. Here is an unconstrained field. This is a ISO 4 vector, but unconstrained. So these are 4 real scalar fields, totally unconstrained. You can add them, take linear combinations, you'll get the same type. But we put in a potential, and we try to write something which has got only couplings which are dimension greater than or equal to 0. That uniquely puts us in the Mexican hat potential. Okay. So here is a dimensionless coupling. This other guy is secretly some sort of a mass term. There's an overall constant here. This is it. This is the renormalizable version. We all know what it is. And at low energies, you look at the equations of motion, where at low energies the derivative terms in the equation of motion are not as important. For the deviation of phi from being a unit vector, we find, so at low energies, phi is approximately Vn. This is the solution. The angular choice of where n points is a massless field, and those are nothing but our pions. The Goldstone bosons of this symmetry breaking. But the radial direction, moving away from this constraint, the moving away from this constraint is massive. It's the Higgs boson direction. And when we do it, even the non-gauge interactions in this arc C Davis becomes renormalizable. We don't have to deal with the nonlinear sigma model. Great. So there are many equivalent ways of writing this theory. This is particularly simple to picture, but you can also write it as d mu h dagger d mu h minus lambda. Where h is a doublet of SU2 left, which is the Electroweak group. So this is the standard textbook Higgs doublet theory that you know and love. The SU2 right action, how it transforms under SU2 right, is obscured here. So this notation, you can do it. By the way, I like very much this book. It's an old book, but the structure of the standard model is quite old. This book, Weak Interactions, by Georgi, which I believe is on his website. I think I recently checked. It's on his website, so you can just read it online. I find it a very insightful introduction to the standard model. It goes through, in some sense, all the different ways of writing the Higgs field. So, in fact, one thing that this doublet notation makes manifest is, or once we realize that this is secretly a rewriting of this, so this H is secretly rewriting, it's a complex doublet, and here are 4 real fields, and secretly it's phi 1 plus I phi 2, phi 4 plus I phi 3. So this is the secret to how it's rewriting this. So obviously, since it's just a rewriting all of SO4, SU2 right acts on these fields and so on. But it's insightful to see that in this way of writing it, once you give me this Higgs doublet, I insist on only SU2 left invariance. If I insist on only SU2 left invariance, if it's a Higgs doublet, and I write the renormalizable potential, automatically, whether I like it or not, this action is equal to this, and we see that this action actually has a bigger symmetry, which is SO4, namely SU2 left cross SU2 right. Okay. So this SU2 left cross SU2 right, which ultimately gives us this SU2 diagonal, automatically comes once we have the Higgs doublet structure. So we'll discuss the significance of that a little later. Okay, where are we? Good. So what we've concluded is, if you put all of those pieces of my story together, you end up with a renormalizable Electroweak theory with dimensionless couplings, this lambda. Okay, dimensionless couplings. Okay, dimensionless couplings, and life is good. The theory can be extrapolated to IMUs. The fact that in canonical normalization that these fields, either phi or h equivalently, have dimension 1, scale dimension 1 as usual for linear fields, means that what we started with, if you ask what did we accomplish, we started with a mass term, and in classic textbook fashion, it's turned into, it comes out of here, okay? It used to be, in Stuckelberg form, it was like this, where the sigma is still dimensionless, but we just put the v squared there. But after we linearize the nonlinear sigma model, it just turns into this, or rather, it's contained inside here, when we give the Higgs of Bev, standard language. And this means that a dimension 2 operator has turned into a dimension 4 operator. Okay. So now we can understand this statement that I made at the beginning when I said, what was the little piece of data that these people looked at? They said, oh, it looks like the masses violate gauge invariance. They didn't know the Stuckelberg trick first. Maybe it was an experimentalist talking. He didn't know the Stuckelberg trick. So he said, oh, it looks like it's violating gauge invariance. And yet the gauge interactions seem to preserve gauge invariance. What do I mean by that operationally? How do the experimentalists say something like, it seems like I have gauge invariant interactions? Well, when you include fermions, which we'll talk about in a little bit, you might look at weak interactions. Of course, at low energies, the exchange of a W gives you the 4 Fermi interaction, etc. Right? But just lost my train of thought. Yes. Once I measure NW, using G Fermi, I can extract this coupling G. Okay. Let me call it G psi, because it's the coupling to fermions. But gauge invariance of interactions, again, from a theorist point of view, you'd say gauge invariant interactions means that you should have that G psi should equal GW, where GW is the coefficient of a non-abelian coupling. For example, somewhere in the standard non-abelian gauge theory, you'll have couplings that look like A and D mu, W, U, B, and W, U, C, and epsilon A, B, C. You'll have couplings that look like this. And what we're saying is, if non-abelian gauge symmetry is true, then this coupling, G psi, should be this coupling, GW. Okay? And the experimentalist, as they work through all the different things, can actually tell whether this is true or not. And experimentally, these kind of relations are true. Let me put approximately, because nothing in experiment is known to be exact. But it's at least approximately. And you could say, okay, fine. So there's some sort of operational meaning to saying that gauge invariance is true in the interactions, even though it seems to be broken by mass terms. But why is that? Why is this true? What is the significance of these kind of gauge invariant interactions, even before we look for the actual Higgs boson, or even before we try as theorists to do the Stuckelberg trick? This is some sort of experimental statement, and what is its significance? So in fact, there really is an experimental part of the experimental program is to check whether these kind of triple gauge boson vertices agree with the gauge invariant interaction structure of the standard model or not. Okay. And you can ask again, why is that so significant? And the reason is that as soon as I apply the Stuckelberg trick, suppose they were not equal. Then when you apply the Stuckelberg trick, wherever there's a violation of gauge invariance, you'll end up putting sigmas to fix it. So, for example, some shift, some anomalous shift, if there's some delta G, if this is not equal to this, there's some sort of delta G that looks like this, that the experimentalist can pick out. All right, I'm seeing some delta G. Well, this kind of operator is not coming from gauge invariance. It's something that you can still make look gauge invariance in the Stuckelberg trick, thinking of it as, say, d mu sigma g mu u a I can Stuckelbergize, and I will get something that makes it look perfectly gauge invariant. Look, this is perfectly gauge invariant. Coming out of here, I can get something that looks like this kind of field string. Coming out of these W's, once I put sigma equals identity in unitary gauge, I will get these terms. And so even a deviation from this relation can be made to look as if it's gauge invariant, but gauge invariant involving the sigmas, okay? And now, when I try to linearize the sigma model, why am I trying to linearize? Because I'm interested, is it possible to have a gap? If I want to have a gap, I must linearize the nonlinear sigma model. I know I have to do that. But the price of doing that, where you end up with something that looks like this, so maybe I should say this goes to H. Okay. Because this has dimension 1, sigma had dimension 0, but this has dimension 1, I have to write the coefficient here as something which looks like, I have to give a coupling, let me call it G. Let me call it some other type of G, curly G. Okay? Where this operator with Higgs replacing sigma, if you look at it, it's got dimension 6. So by dimensional analysis, the coupling constant has to be -2. So in order, there's sort of a shifting of problems in this whole story. In order to make sense of gauge interactions with massive, in order to make sense of the interactions of the W boson, we had to push the problem into these nonlinear fields. But then we discovered that this is secretly hiding the problem. It's the same problem. There are strong interactions here, non-normalizable interactions. To get rid of this non-normalizable interactions, we have to linearize the field. But if we have gauge non-invariant interactions, then when we linearize the field, those gauge non-invariant interactions look gauge invariant, but with coupling constant which has negative mass dimension. So this implies that the theory is non-normalizable. Again. Okay? So, if the experimentalists, and as I said, this is not an in theory kind of, this is what they have spent some significant time doing, looking for these kind of deviations in the gauge invariant structure of interactions. If they had seen something, some small delta G, then that would have automatically told them by this reasoning that the electroweak theory cannot be extrapolated to high energies in its current form, or just the particle content that we have seen experimentally. Even after you discovered the Higgs boson, which is today, if they had seen this delta G, the Higgs boson would not save them. In fact, linearizing this is what would give rise to this problem. And even the Higgs boson would still leave you with a non-normalizable theory. And hence the theory would not be extrapolatable to high energies. So, if you posit that there is a gap, then you should expect that this coupling G is 0, or very close to 0. In which case, you would say, I do not expect any deviations in the interactions. I do not expect deviations from gauge invariance. In the naive Unstuckelberg-Eis theory, there should not be any deviations from. Now, this is what I think is called circumstantial evidence in the technical sense, legally. If the implication sign only works one way. If there is a gap, the interactions should be very closely gauge invariant. Experimentally today, we see that the interactions are very gauge invariant. Not by going to high energies and seeing if there's a gap, we just look at energies of order NW and we see that the interactions are highly gauge invariant, which is consistent with a large gap. And therefore we say, gosh, it didn't have to be like that. These couplings could have been anything a priori. It seems like there's, and of course there are many such couplings and many such, it seems like there may well be a gap. Not because we went to high energies and checked yet, but because, to some extent, we've checked, right? LHC, but this evidence is seeming to point to some sort of a gap with indirect evidence. Precision testing of the implications of a gap. The implications of a gap give you a very special structure of interactions. We see that special structure even at low energies, and that's like some fossil evidence that there may be a gap. Now, fossil evidence is dangerous because somebody can carefully orchestrate a dinosaur bone synthesize it, put it on the ground. I think this has happened in history, right? That, and then, or not that, I think it was some sort of human, pretend human bone, ancient human bone. But you can do it, and then if you discover it, you would be fooled. It's just, so you don't know whether this is circumstantial or not, but it's highly suspicious that a gap requires a special structure of couplings, and those are and you see that happening already. Okay. So already our aliens are starting to suspect that there is a gap, and they are starting to resemble us in their thinking, which is the feeling of the field. How big is the gap? For that is beyond the scope of this course, but to say it quickly, our precision on measuring these delta G's, it's not that great. So we may well discover new physics at the LHC, which, however, is consistent with G's. Okay. That is, the LHC is already even if there's a gap, and it's not too big, a factor of 10 or more, the LHC is still sensitive to it. Okay, so even if there's a gap, it's not the end of the world. If it's a very big gap, then the LHC doesn't see it. And these lectures, I'm at least just trying to give the sense of qualitative statements. And your questions may fill it out. So this is why we have our eye on these kinds of gauge invariance statements. I have not, just as a final note on that topic, on this development here, I have not talked about hypercharge. I just stuck to the SU2 aspect and 3-gauge bosons. I never mentioned the photon, I never mentioned the Z and all that. But it's easy to include in this sigma language. So remember, sigma transforms under SU2 left cross SU2 right, like this, to include hypercharge. To include hypercharge, you just need to realize U1 hypercharge as a subgroup of SU2 right. Which subgroup? Namely, the U1 that's generated by tau 3. Who cares which direction? It's one of the U1s sitting inside SU2. Okay, that's it. And as far as the Higgs is concerned, this is true. I'll mention a slight subtlety. This is not always true, and I'll say something. But let me say it now, and I'll have to say it again later. But basically, the true statement is, if you talk about all the fields of the standard model, then hypercharge is really a subgroup of SU2 cross SU2 right, and something called U1 baryon minus lepton number. I'll discuss that a little later, but since the baryon number and lepton number of a Higgs boson, of the Higgs field, is 0, for the purpose of the discussion I've just given, this is good enough. But anyway, it's easy to, as you know, it's easy to generalize the Higgs to include hypercharge. Of course, we know that, and then you get all the usual results. You get a photon, you get a Z. The Z and the photon are mixtures of the hypercharge field and the W field. So go ahead.
So I don't understand how new physics should affect electroweak gauge invariance. Can you understand what?
How? Sorry, physics.
New physics.
New physics. Yes. So whenever you see a non-normalized, so again, the question is where is new physics going to come in? Suppose what's its relation to this breaking of gauge invariance? Suppose there was a little delta G and the experimentalists saw it, and then some theorist quickly swoops in and says, delta G, well, it's not a breaking of gauge invariance. It's really, it can be Stuckelbergized, but that would say it like this, but then in an attempted renormalizable theory, or if you like, linearizing the nonlinear sigma model, I end up with this statement, and that means that there's a coupling in the theory, and secretly, this little delta G is secretly a big G, and it's non-normalizable. Okay. First, that's it. Now, if that happens in the real world, If it happens on a piece of paper, you can always say your theory is non-normalizable, it makes no sense, go away. If it happens in the real world, you can't say it makes no sense, it just happened. Somewhere, this non-normalizable theory must have a UV completion of some sort. That means that operators like this, which are dimension 6, there must be some way where there's some G mu nu, and then there's some, so they're the let me do it like this. There could be, here are my W's. There must be some story where there's new physics, which is heavy, and maybe breaks, and is sensitive to electroweak symmetry breaking. This is drawing the VEV of the Higgs field. And because it's a heavy particle, so that at low energies, the particle cannot propagate very far in space-time, this thing is approximately a point. And in the low energy approximation where it's a point, in low energies where it's a point, it looks like this effective operator, and the effective operator is nothing but this. Okay. So whenever we see a non-normalizable theory experimentally in our face, we have no choice but to believe that somewhere there are some new particles, which if you get rid of them, in the sense that you say that their effects at low energies are short distance, and you are sort of breaking this diagram down to this. This theory, all the couplings here, may be perfectly normalizable. And yet, in the approximation that you throw away this heavy particle and keep its low energy effect as a kind of contact term, point-like interaction, the theory becomes non-normalizable. This must be what's going on. Hence, I have reason to be hopeful that the new physics is there. And that the thing that this G is really something that is proportional to 1 over the mass of the new physics. Something like that. Okay. Thanks.
And why the implication is also the opposite way. You say if there is no gauge violation, then there should be a mathematical.
Now this is not a theorem, meaning it follows from no logic. It is, however, the way we all operate in our real life, and but it's much more dangerous. That's, I think, what is called circumstantial evidence. That is, I see no reason why these couplings should be gauge invariant. Gauge invariance is absolutely crucial if M equals 0, MW equals 0. We better have it, but it's not 0. So I see no reason why the theory should, especially if there's no gap. I have no way of arguing for you that these interactions should be gauge invariant. They don't have to be. And yet the fact that they are is so consistent with the existence of a gap in a non-trivial way that you at least are worried or suspicious that there is a gap. But it is not a proof. Your neighbor's boy is very naughty. Your window is broken, and it's the window facing your neighbor's house. That proves not. That's the nature of circumstantial evidence. By the way, this happens if you're a parent. I mean, this happens all the time. The circumstantial evidence in favor of the fact that your child has done something bad all lines up, but you can't prove it. But it doesn't matter because you are a dictator. You convict them anyway. But we're gambling. That's the point. We're gambling. Gap, no gap, no gap. We're gambling. Of course, to gamble really well, you should understand how sensitive and what are the error bars and blah, blah, blah. Okay? So you need to do many more exercises than I have time to do here. But a lot of what people, if you go through, people write some papers, and that is like 1% of the work that they've done. because they're going through all the different exercises, talking over lunch, and all of that meditation that they're doing before they write that 1% something that gets published is these exercises. How big is the delta G if I have a new particle whose mass is 1 TeV? Am I sensitive to that 1 TeV particle at the LHC? Wait a second. Would I already be sensitive to it at LEP2 by having checked some coupling at low energies but with high precision? This is what everybody is doing in research. Then occasionally they find something that hasn't been noticed, and that's the paper. Again, Roberto and I were talking about recent events and testing the Higgs boson and so on, in this kind of precision sense. And it's a subtle conversation. People are doing a lot of exercises. They can do it with great art and great intelligence and economy of thought. They can do it in a dumb way. Most work is, of course, done in a dumb way. And there's a lot of room for being brilliant in even just this kind of discussion between experiments, even when the experiment is null, even when the experiment didn't find a deviation from the standard model, the significance of the error bars for new physics is somebody has to do the research to figure out what that is. That requires intelligent, and as time evolves, it requires a new thinking on that, because the experiments change their error bars. A recent thing, the Planck satellite has now produced new, details, precision information about the cosmic microwave background. So calculations which were kind of state-of-the-art before are no longer have the precision to match the experiments. So there are a number of interesting effects where I was just told by one of my colleagues that apparently a photon traveling through the universe, of course, they have to keep track of the fact that it travels, when we see the expansion of the universe or the acceleration of the universe, light is coming from some supernova far away, it comes to the Earth, Hubble Space Telescope, whatever it is, or the Planck satellite. When we keep track of these kinds of things, you use an approximation. The universe is homogeneous, roughly, okay? But then, if the experiment is so detailed that even the inhomogeneities have to be considered, we have to take into account that approximately it's uniform, but then there are deviations from that. Then it requires a new calculation, and often a subtler calculation. So this is happening all the time in terms of what's the research that's going to happen in your period of graduate school. There's going to be, at the very minimum, maximum, experiments, the minimum. This kind of work is necessary and has to be done, and covers a large base of experiments, some of which are not even LHC, maybe, or even earlier collider experiments, maybe dark matter experiments, and so on. Very good. So let's shift to a slightly pheno side, namely this thing that was, so we did recently discover the thing that's different between the linear sigma model and the nonlinear sigma model, the so-called sigma field, the Higgs. Okay. And we are confidently told now, this is the 126 GeV thing that they discovered at the LHC a couple of years ago, year and a half ago. And obviously we now understand that it plays the absolutely central role. It is a prediction of a gap. It's the prediction of a gap. That doesn't prove that there is a gap, but if there was a gap, you'd have to have one of these. Okay? And even that's not quite true. If there was a gap, and the theory can be studied, even in the UV, can be studied at weak coupling for all these techniques of normalizability that we use, it would predict this. If you flip it around as a gambler, you might say, I suspect that maybe we have a gap, and the theory is that the standard model is weakly coupled to some high energies. That is not a logical consequence, but think that. And only after the discovery of this can we even guess in that way. Okay? Because if it didn't exist, then there has to be something else has to happen. It's interesting because it's j equals 0. If you believe the standard model, if you believe the gap hypothesis, which is what I really mean by saying the standard model, if you believe the gap hypothesis, that H is an elementary, which is to say point-like particle. Okay, because that's the way we've been treating it. We've been treating it using fundamental quantum field theory techniques. And it's an elementary point-like particle for the first time. After all, pi 0, or it's a pion of QCD, is composite. So when I say elementary, I mean it in contrast to the idea that we have seen spin j equals 0 particles exist, like the pion is a j equals 0 particle. But this is the first one that if you believe in a gap, a very large gap, then this Higgs boson is actually an elementary particle. The first one today. By the way, one has to just think for a second how many fermions you've seen in nature. How many spin 2 you've seen in nature. There are some that are massless, gravity. We haven't seen the particle, but we've at least seen the wave associated with the particle. Effectively. We haven't seen the wave very directly, but we've seen very indirect evidence quantitatively pointing to gravitational waves. We have seen massive spin 2 particles, but they're composites of QCD as well. We've seen a number of different types of spin 1 particles in the sense that we see gluons, in that non-abelian sense, the massive theories of W and Z, the electromagnetic gluon and so on. But we haven't seen j equals 0 elementary before. We've seen the massive, we've seen the composite, but we haven't seen j equals 0. Even here, it at least stands out as an odd thing. You might say, heck, I haven't seen j equals 7 either. Or j equals 7 halves, to simplify my story. I haven't seen this either. But you have. Actually, these are also composites of QCD. You might say, but they're not elementary. And it turns out because there's a theorem. The theorem is that spins bigger than 2 cannot be elementary. You may have noticed that when I was doing the massless theories, that with j equals 1, we figured out gauge invariance. Of course, there are different types of gauge groups and so on and so forth. When you go to j equals 2, boom, it's got to be general relativity. There's nothing else. It's already so tight. The game is so tight. If you go to massless spin equals 3, doesn't exist. Self-interacting massless spin, I won't do it, you can play around with it. Doesn't exist. Okay? So these higher spins, just theoretical consistency is killing j. And of course, you might say, but it could be massive. But if it's massive, and then if I go to, and suppose it's not composite, and it's a massive particle with high spin, I can go to high energies, and the theory should extrapolate because it's you're saying it's some sort of point particle, so I can continue to see this particle. Even as I hit it harder and harder and harder, it continues to look like j equals 7 halves. Okay? But if that's true, we've just seen that in some sense the notions of gauge invariance associated with higher spins have to continue. It has to, at high energies, even this massive particle should look like a massless particle with high spin. But massless particles with high spin are theoretically inconsistent. So the only kind of massive high spin particle that can exist is one which it exists, but if you kick it a little bit, you see that it's not, you cannot extrapolate to very high momentum transfers. It starts to break up. What's the name for some particle that breaks up when you kick it a little bit? Composite. Okay? That's the operational meaning of composite. So it's not surprising. Nature has given us every trick in the book. Boom, 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 boom. And even these composite high-spin particles, it gives us all of those. It couldn't give you an elementary spin 7.5 particle because it's theoretically impossible. Spin 0, it could have given you an elementary spin 0 particle, but it is significant that giving you so many riches, this is the first time that we would have an elementary spin 0 particle. If you believe there's a gap, maybe there's no gap, maybe even this is just like a pi on some composite of something, okay? That is an experimentally open question, and a very significant question we'll talk about in the later lectures. By the way, there is one missing piece in what is theoretically possible. It is theoretically possible to have a j equals 3/2, m equals 0, or at least m much, much lighter than the Planck scale. This is a theoretically possible theory, but like spin 2, it is incredibly constrained by theoretical consistency. And it uniquely points to the theory of supergravity. Okay, it requires supersymmetry, and it requires supersymmetry in the presence of general relativity. Otherwise, this thing wouldn't make sense. And the same kind of consideration, if you want to see the baby version of it, the same kind of considerations in my first lecture for electromagnetism or for linearized gravity that I did will give you the same linearized supergravity conditions that you're attacking this problem. You'll have to think a little bit how to frame it, but the linearized level, just doing free field theory of this, you should be able to see something. So we haven't seen this either. You might ask, why not? Nature gives us everything. It seems like this universe that we've come to seems to like use every trick in the quantum field theory book to populate things which are light. Everything you can have is given to you. Not pick this, pick that. No, just give me everything. Okay. But it didn't give us this. Okay. Or even this. Very light gravity. This then becomes the gravitino of this theory, the superpartner of gravity. In fact, if you have this, then you sort of need the gravity. Why hasn't nature given us this? Well, actually, how do we know? It could be very light, could be 1 GeV, but it's not a boson. It uniquely has to be the gravitino, which means it has couplings that are Planck suppressed. Just like it's got G Newton somewhere in there in terms of its couplings. That means it's incredibly weakly coupled at low energies. So maybe we just didn't see it. But wait, if you can say that G Newton is so small at low energies that we can't see the gravitino even if it's there, why doesn't that apply to the gravitational field? Well, the gravitational field is a boson, so we can make very big gravitational fields by putting lots of bosons together. That's not an option for the gravitino, which is a fermion. And so you see, there's a plausible reason why this could be sitting amongst us, and yet we haven't seen it. It has no choice. It cannot be super strongly coupled. Okay? Even modestly strongly coupled. Unless it's a composite, in which case it's not the gravitino, it's, what is it, delta or something? Delta of QCD or something, right? So, keep your eye on this fact, that there are some gaps in our, this is only tentatively, because we don't know for sure that there's a big gap, this is only tentatively an elementary particle, and it's a first, when we have so many other types of spins. And the gravitino may actually be there and be elementary and be even kinematically available to us, and yet so weakly coupled that it is not an easy thing to find. Of course, gravitinos may be sitting in decay products of the LHC. It's possible. Okay, let's get back to this particle. The standard model, what does it say? I want to kind of make, just give you the quickest introduction to the richness of Higgs physics, maybe. So this is the Higgs particle as in contrast to the Higgs mechanism. This is the thing that's mandated not by gauge invariance, it's mandated by the extrapolatability of the electroweak physics. So why is it rich? Because there are some tree level. It's rich because there are a lot of couplings to the Higgs. And a lot of these couplings are visible right now or in your lifetime. Okay? And so there's so many of these. This is a particle that doesn't just talk to a handful, it talks to everybody. In that sense, this is the most sociable of particles. And so there are couplings like this. You're not surprised because it comes out of the d mu h squared. You can take two z's from here. You can take one h from here, and the other h, the other capital H, you can set to the VEV. Okay, if you want. The VEV of the Higgs field and the fluctuation of the Higgs field. So you have this kind of coupling. Or it could be W's, just as much. This would be rather important because it allows the Higgs to decay. If it was a very heavy Higgs, it could decay to 2 Z's. Even if it's the Higgs that it is, it can't decay to 2 Z's on shell, but the Z can be off shell, and these things can go to leptons, charged leptons. So this is one of the most spectacular of the final states decays of the Higgs. When you produce a Higgs, which is a rare event, its decays include even this 126 GeV guy, 4 leptons, 4 charged leptons, which is a rare thing to produce of the LHC, hadrons, QCD, color, protons, all that kind of stuff. But leptons are harder to come by because it can only come by some sort of electroweak process or in the middle of jets because of the decays of some heavy hadrons. But isolated leptons, away from the decay of the B meson or anything like that, is harder to come by, and so 4 of them is spectacular. Which hopefully leads into the Matt Strasser lectures on applied physics. Hot thing. Then another one. You're not surprised to learn that I missed something very important in my order of presentation. Let's see. And I put this on hold. Yes, I gotta put it on hold. I'm about to talk about the fermions. How can I talk about the fermions unless I said something about them? So let me say just a few quick remarks. Fermions. Okay. Again, the interactions are gauge invariant in the sense that I said that the gauge field, this gauge self-interactions are gauge invariant interactions. The same thing. And gauge non-invariant
masses. The same thing happens. And what does this mean? This gauge non-invariant masses is very important. You should compare it with QED, where the Dirac mass of QED, that this mass term, this psi bar psi, is gauge invariant. Okay? Fully consistent with the gauge invariance. But rather significantly, just like the W boson mass, you can't write down the mass term for fermions that we've seen so as to be gauge invariant. And so we all know how that works if you've studied, taking the basic course in electroweak theory. That psi bar psi, if you break it up, a Dirac mass looks like this. So in 4-component notation, if I break it up into 2-component Weil notation, it looks like this. And it's these things, in the standard model, it's these left-handed guys that are electroweak doublets. And these things are singlets. So that these mass terms, if you put an M in front, break gauge invariance, and by Struckelbergizing and then linearizing the nonlinear sigma model and so on, end up having to have the Higgs here in some way. Okay? That's the only thing. So this is very special because in principle, one can contemplate physics. One can, unlike the gauge bosons, you can write down matter. You can choose matter such that psi left and psi right have same electroweak charges. So it could have been that the left and right pieces that make up mass terms could have had the same electroweak charges so that psi bar psi was gauge invariant. But that's a new possibility that wasn't present for the gauge bosons, which could a mass term in gauge bosons. A mass term of the spin 1 guys will always break gauge invariance. But for the fermions, there was this option, and nature chose not to use it. We have not seen any particles, any fermions, where the mass term can be written without invoking something that breaks electroweak symmetry, namely the Higgs. Okay? So this statement has a name. When you cannot write mass terms which are gauge invariant, that is what is called a chiral gauge statement. And the name is obvious. It's chiral because there's a handedness to the assignment of the electroweak quantum numbers. This handedness has different quantum numbers from this handedness, so the Dirac mass term option is dead. There's no mass term that's consistent with electroweak symmetry. And it did not have to be so. Okay? We could have imagined something else, and I will remind you in a short while of some examples of something else. Okay? So this must be taken as an incredible clue. And the way to see how sharp this miracle is, that something is being told to us by nature, is to say, so I'm going to keep this, I come back to this, but is to say, if in chiral gauge theory, if we don't have Higgs multiplets, we don't have the Higgs physics and the Higgs mechanism, then both gauge bosons, then both J equals 1 becomes massless. I mean, you can have your massless gauge bosons. They don't have any Higgses to give them mass. They're massless gauge bosons. And that's got that digital robustness that I was talking about, because the Higgs bosons are the things that supply the extra degrees of freedom to make 2 polarizations into 3 by eating those pions. So this is digitally robust. But once you have the gauge theory being digitally robust, because once it's massless spin 1, you must have gauge symmetry for the field theory description of it. But if you have chiral gauge theory, the quantum numbers of the fermions are chiral, then even the spin half guys are massless with digital robustness. The logic is not about counting degrees of freedom for the fermions. It's the statement that once we see that the spin 1 guys are robustly massless, they must be described by a gauge symmetry. And if the gauge symmetry acts on the fermions in this chiral way, the definition of chiral is such that you can't write mass terms, and hence they are also massless. So this is a very powerful mechanism, and it seems to be being used in the spectrum of the lightest states. As soon as I do have, of course we do have this Higgs degree of freedom, it seems to be acting only, because it's such light particles compared to the it seems to be acting to give mass in a story which is predominantly just this. After all, electroweak symmetry breaking is a piddling and small effect compared to things that really matter on the Planck scale, right? It seems to be acting to take the rules. What does it mean that the rules are that you take a theory which has this kind of digital robustness, as if you're just not allowed to write whatever you want. Why do you need this digital robustness? Why don't you just write, why does the nature just choose the couplings and masses and make them small if it wants to? But it's doing it in a way with this very tight mechanism, which you should play around with if you have. And then it's dirtying it up just a little bit with the Higgs mechanism. And as I said, this has nothing to do with being extrapolatable. You can have perfectly normalizable theories where the left and right components have the same quantum numbers. That does not obstruct you from, this is a completely separate issue from extrapolation. You could have had this, but we don't see it in nature, and it has nothing to do with whether you can extrapolate or not, but it does have to do with this digital robustness. So I think this is a profound clue about something, but exactly what we don't know. Because of this, all standard model masses, all standard model masses are proportional to, they're all of the form coupling times V. Even the Higgs boson, even the mass of the Higgs goes like lambda V. Okay? Textbook stuff, you work out the line volume potential, you look at the quadratic term or the physical Higgs and you find this. Everything, the fermion masses look like some Yukawa coupling times V. The mass of the W looks like G times V. Everything is proportional to V. So there's a puzzling form here. It seems to say that the lightness of these particles, we could understand why all of them are light if we just understand why V is small compared to M pi. It's like nature is giving us some mechanism which says, don't ask why this guy is light, why is Joe light, Fred is heavy. You don't have to ask all those questions. They're all light get them all if you just answer one question. Why is the weak scale small? And yet, the weak scale, the irony is that in the standard model, there's no reason why the weak scale is small. In the standard model, if you just look at that line bubble potential, if I had said it was this, or this over 10, it's okay. But it seems to at least unify all the puzzles. The puzzles are, why is this guy like, why is this guy like, why is this guy like, why is this? It's all unified. This mechanism is so tight of chiral gauge theory that the answer to all of them is one question, and why is this thing like? And yet the standard model doesn't explain why this is right. And you can see that because this v squared, when you write lambda h dagger a equals minus v squared, the v squared contains, so this potential contains some minus v squared lambda, the so-called tachyonic mass term of the Higgs doublet, the thing that causes it to get a bev, okay? Negative mass square of the Higgs. That's where V, that's the only place V occurs. There's some overall V to the fourth constant potential, but constant potential in field theory is irrelevant. So this is the only place it appears. And this doesn't have any rigid, this does not have any digital robustness, no nothing, because for these scalar fields, this is completely gauge invariant. Okay. The mass term of scalars is automatically, you can always write a totally gauge invariant mass term. Unlike for fermions, where I don't care whether you use all left-handed notation, left, right, whatever notation you're used to, the physical statement is there are quantum numbers for fermionic fields such that no mass term is gauge invariant. But this is not true for scalars. This is where the weak scale enters, and indeed anything could have been used. Okay? So something weird is happening in the standard model, that it has digital robustness for all the relative mass scales. They're all, everybody moves together in some way, because they're all proportional to V, and yet the V is missing this digital robustness. Okay? So let me make a comment. I want to get back to the Higgs pheno again, but let me make a comment about let me make a comment about the beauty of supersymmetry and the flaw in the MSSM. Okay. So, I don't have much to say about Susie during these lectures, but I want to say at least the biggest of the biggest statements that could be made. In Susie, if the world was supersymmetric with all the same physics that we just talked about, okay, add supersymmetry, then this Higgs would be paired by supersymmetry with the Higgsino multiplet, which is a fermion still. Opposites of this. It's fermion. Okay. And this is very clever. You see, this might be the germs of an idea, because this, of course, implies the degeneracy, by which I mean, even in the Lagrange, the masses have to be related to each other, the mass of this and the mass of this. This is a fermion. Mass terms could be protected by the sort of chiral nature of this fermion. And that would have to be inherited by supersymmetry with this. Okay. So, related. quotes because you can think of this as some sort of a kind of a mass term, but it's got the wrong sign, and so eventually you have to go to a new vacuum state and expand. And so, but ultimately, from a very high energy perspective, it looks like some sort of mass term. But in supersymmetry, it cannot just move by itself. It has to move with this. So in principle, if you have a certain chiral symmetry for the Higgsino, then you'd be in great shape. Okay? But that's where things get ugly in the practical world of supersymmetry. Still might be true, but in terms of the highest standards by which the standard model data is coming out, something goes wrong in this plot in the following sense. That the Higgsino comes in two types. There's Higgsino up and Higgsino down. Okay? It turns out that they're in supersymmetry for reasons we'll talk about a little later. But there are two Higgs multiplets, two Higgs boson multiplets, and two Higgsino multiplets. And these things are a non-chiral. These are precisely an example of a non-chiral fermions. Meaning you can write a perfectly gauge invariant you can do it. There's no problem writing this. It's like a Dirac master. Okay? So for the Higgsino, you can actually write a Dirac master. It's consistent with the gauge symmetry. It doesn't have the same digital robustness that the chiral gauge theory of the standard model has. So at first sight, you say, gosh, then maybe this is M-Planck. That's completely consistent with supersymmetry. In which case, it would not be of much use. Then you won't have Higgs boson in nature. Okay. Can we invent a chiral symmetry to stop this? Well, we can invent a chiral global symmetry, which, who knows, maybe it might be the remnant of some gauge symmetry way up at high energies. That's easy. It's just this. It's called Peche-Quinn symmetry, because it's related to the story of axioms and so on and so on, which Peche and Quinn were central to. But Peche-Quinn symmetry is incredibly simple. It's just H up and H down transform like e to the I alpha H up. It's just a U1 symmetry like this. And if they both transform the same way, then this I didn't put dagger for various theoretic reasons. This is the mass term. If they both transform the same way, then this thing is not invariant. Okay? By the way, in this language, you might say, wait, shouldn't I think of this as left-handed and this is right-handed? No. In this funny supersymmetric notation, both fields are left-handed. So in purely left-handed notation, this is the mass term, and in this symmetry, the mass term is not invariant. So if Peche-Quinn symmetry has some legitimacy at very high energies, this, that, and the other, and says you're not allowed to violate Peche-Quinn symmetry, then you put a 0 here. And now we would understand in supersymmetry why the Higgs, then this gives back our digital, only if you understood what the root of, we can't understand this Peche-Quinn symmetry at low energies as any sort of gauge symmetry. Maybe at high energies there's some different story. But once we have it, once we put that 0 there, then this field and this field both end up being very light. In fact, if you don't break supersymmetry in the MSSM, if you don't break supersymmetry and you put 0 here, very beautifully you can have electroweak symmetry break. Okay? Even the supersymmetric level. That's because the potential for the Higgs looks like this. You're all used to the potential looking like this, right? Here it looks like this. So this is a perfectly good place to, this is a Higgs equals constant here is a perfectly good ground state. so is Higgs equals 0. There's no predictive value. It's not like here where you have to live somewhere on this rim. In this theory, you could live there, you could live there, you could live all the way up at M Planck. So again, the supersymmetric theory is intriguing because it relates the spin 0 to higher spins. It's intriguing because you can even try and give some sort of chiral sense to the fermions to protect them, and hence, by supersymmetry, to protect the Higgs. And yet, there's no simple version like this where you can directly see, I automatically get the weak scale to be small compared to the Planck scale by some tight qualitative reason. And indeed, in all the, if you talk to the expert supersymmetry model builders, they spend a lot of time worrying about this term and why, in fact, it's not. Why is it 0? Why is it, if it's not 0, why is it small? Why is it not M Planck? They find various rules to get around that, but it's bothering them. This thing has a name. It's called the mu problem. And it worries people why there's this issue. It is one of the uglinesses of supersymmetry in its MSSM form, and we wish we had some better understanding. That doesn't mean it can't be solved. I'm just saying it's something that is slightly in the end, the fate of supersymmetry and electroweak symmetry breaking all comes down to supersymmetry breaking, which is off the, I'm not talking about it, but maybe you have had David Sheep telling you at least a little bit about it, I'm not sure. Okay, so whatever magic Susie has is how in fact it got broken. Because the supersymmetric limit has some intriguing features, but it does not by itself just nail this. Back to, did I start late? Did I not start late? Okay. So let's just see what other treat. Well, here, at least I can tell you, right? So there's the Higgs, they're fermions in some way, and these are the Yukawa couplings of the fermions. In particular, the big Yukawa couplings are for the top or the bottom to a lesser extent, because masses are proportional to the coupling to the Higgs. The heaviest fermions we have are the top and the bottom. And part of the richness, so let me just stop at that list, but part of the richness at loop level, the loop level, turns out to be very important. In other words, even the 0th order attempt, just don't do precision Higgs measurements, just find the damn thing. But already we are forced to do loops. This is not like your typical particle where you just do tree level and then discover. Already we're forced to do loops. Because to create this particle, I don't easily have access to these W's and Z's in my initial state. And I don't easily have access to tops and bottoms in my protons. So in some sense, doing this is forced on you, at least as a significant player in your production, where you take gluons from the protons, smash them together, use the top quark loop, which has a big coupling to the Higgs. So a virtual top is being used to create the Higgs. And then in the phenomenology, the Higgs can't decay to TT bar because it's too light. It can decay to BB bar, but there's lots of background processes that produce BB bar. It can go, it's hard to go, it can go to these 4 leptons, that's pretty spectacular, but because the Higgs is light, these are off-shell Z's, and the rate is very small, so you've got something happening, but at a very small rate. It would be nice to have some other beautiful background, relatively background free, actually there's lots of background, like somewhat muted background process that you can look for. And in fact, this virtual W, it's a stunning fact, this virtual electroweak diagram of such great subtlety, a W loop, allows you to look for Higgs decays to 2 photons. This is where some of the first evidence for Higgs came from. Where the Higgs can, of course, you can't produce it like this if you don't have that beam of photons, okay? But the decays to photons is very important and mediated by this W loop. Or you could replace one of the W's by a Z, and you could have photon Z. Okay, that's something great to look for. Or you can compare this channel with the Higgs decaying like this to this channel with the Higgs decaying like this, and you can compare the rates. These are all things sitting in the standard model. So, the standard model Higgs, even if you don't think of anything beyond the standard model, is already incredibly rich because it does couple to gluons. So there are big cross sections for producing the Higgs. There are other ways to produce the Higgs. You can actually use this coupling with the W's there to take quarks from the protons, in some sense these off-shell W's. So quarks from protons can give rise to this diagram for producing the Higgs. This is also a significant player. So there are multiple production mechanisms of great subtlety. Okay. There are multiple, you can look for muons eventually if you're the White Magic Collider, or you're figure out a new plan, alias, I don't know, whatever. So there are incredibly rich decay modes, incredibly rich production modes. You don't get a better particle, forget the theory, you don't get a better particle for phenomenology than the Higgs boson. Okay. And so let me just end with today with the moral that I find very tantalizing. Can I take till that number hits 7? Just the moral is, of course, there's a moral in the discovery of the Higgs, but I consider that there's a very great moral in the non-discovery of the Higgs. Okay, the non-discovery of the Higgs is the, I think, unappreciated story, perhaps if you're young enough, the unappreciated story that needs to be appreciated because it's at least as important as the discovery of the Higgs, okay, which is textbook. Okay, these are all very nice, but they were written down sometime. The non-discovery of the Higgs is, look, we already tried. See, here's E plus E minus machines like the Lep experiments. Okay? You could have a Z, of course, you could have the Z decay into the Higgs if the Higgs was light enough. Say at Lep 2, that was already off. You were using the Z as an off-shell particle, but you're using that coupling up there to do something like that. And then you could look for a BB bar or something. Okay? Now, this of course was done and it put some bounds that really were saying that the Higgs is heavier than 115 GeV, right? That's where the Lep ended. In principle, you could have said, wait, kinematically, Lep 2 could have done better. It could have, you could take this to be off shell and let it decay. In which case, the Higgs could actually have, kinematically, the Higgs could have been heavier, of order 200 GeV, and kinematically, this final state would have been perfectly doable. Okay. But because once this is off shell, the amplitude is so suppressed that quickly becomes not practical. But not for a kinematic reason, but because you might say all the couplings here are all order 1. You can't tell me that this is a weakly coupled anything. But just because of the amount of phase space that, I put if this is off shell, then it's effectively a 3-body phase space. This becomes suppressed enough for practical reasons that you don't see it. And so you don't see the Higgs at LEP 2, even though kinematically it is conceivable that you could have seen it. And all the couplings look like they're ones. If you look at the Lagrangian, you say, I don't see anything that's one. It's not a neutrino, it's the Higgs. Then we can look at Tavitron. Okay? Tavitron is very interesting because the dominant cross-section already takes over to be this. This is the quarks and the proton produce, or gluons are sitting inside the proton, and this thing is what produces the Higgs. This is the dominant cross-section. But these decays to BB bar, or even to W star, through this coupling, are already two. So there's some regime. If the Higgs was very heavy, the WW channel would have been discovered, and they put bounds in that way. But the actual value of the Higgs came out to be the W's were just not seeing enough of it to see evidence. And the BB bar has so much background from QCD that you don't see it. So Tavitron loses its Nobel Prize. Why? It's operating at pretty high, what is it, 2 TeV or something? So it's operating at incredibly high energies, way, 10 times bigger, 20 times bigger than the actual Higgs mass turns out to be. It's a hadron collider, tons of cross-section. It's got the same coupling that we end up using in LHC to discover it. It does not see the Higgs boson. Is it because the Higgs boson doesn't have a lot of coupling, big cross? No. It's got everything going for it. This is the richest particle in the history of physics. It just doesn't get better than this. But maybe the top one. But you still miss out on seeing it for no kinematic reason, but because of the details. In other words, you must work, I can't say it fast enough, but you have to work through a little bit how these things didn't happen, how these discoveries did not happen, to appreciate the art of hunting for new physics. This is old physics in the sense that we at least had the plan of what it looked like. Even when we get to the LHC, from my discussions with some experimentalists, it really mattered that we knew we've eliminated the high energy renormalizable Higgs theory, we've eliminated the low energy renormalizable Higgs theory. If the Higgs is in this little gap around 120 GeV, then we should look for these 4 leptons. But normally, if I were doing some new physics to 4 leptons, I would ask that these leptons were highly energetic so they could kill a lot of background. But this time, since I know I'm looking for 120 GeV, which has to be shared by these 4 leptons, I will set my thresholds a little lower just so that I capture this guy. Similarly, if you look at this picture and you look at the shape of the background, it's very hard without the enhanced picture that they often show to see the gamma-gamma bump due to the Higgs. Okay, it's really, you would scarcely trust that this is a discovery if you looked at the raw data. But you put everything into the discovery because you know the standard model stands for something. Gap. Okay, it has significance theory. It means gap. So because the gap implies these consequences, you look like crazy. And then you see evidence for this guy. Okay? Even though people sometimes say 4 leptons, that's so spectacular, but actually it's a fairly light particle by the standards of the LHC going to 4 leptons. So it's not as obvious that you would have seen it if you didn't know to try to look. Okay? So this non-discovery story I think is very important because we may be facing new physics which is within the LHC grasp. But because we don't know in advance what we're looking for with the same certainty as the Higgs. Everybody has a pet theory, but they're pets. They are not as grand as the Higgs boson. Because we don't have that, we may not know how hard to try, even this 4 lepton. How hard should you try? How hard should you try to really see if that bump is there? If you don't know how hard to try, then you might not try that hard, and you might be sitting on it, and it's not, and you see nothing. Okay. Even this shows you how tricky a rich particle can be. If it's not as richly endowed as the Higgs, who knows? But it requires ingenuity, and that's why I'm taking a little extra time only to say that that's where you come in. Unless you understand, I'm mumbling in this slide, but unless you understand what it is that I have in my head that's the problem, which is, as a practical issue, we are hunting for something new. The thing we're hunting for is not quite known to us. None of our theories have stood the test of time beautifully well. And we need some new ingenuity. The ingenuity is both practical, how do you hunt in the midst of background, and also theoretical, what should you hunt for? I think there's still room for new ideas, that's where you guys come. Okay, so we stop there and then take over tomorrow. I should say, not stop, I'm open.